Okay, this is part two of the calorimetry discussion. This is where we're going to actually go through some problems. This is the handout that the pre-AP students will get this year. AP students will have the same front page, but it'll have a different set of problems to work. The equation I have on the paper here is just one I found from ClipArt online. It's not in the greatest order. What I was really trying to get here was Q equals M, and I do it C sub P delta T. So the order is a little different, and I input the P there. So let me explain real quickly, in case you missed it in class, why I use C sub P. What it means, first of all, the P is pressure. It's constant pressure specific heat. Most things in chemistry we do on the desktop, we're doing it at atmospheric pressure, which is mostly constant under all but extraordinary situations in class or in the lab. So we can really ignore changes in pressure. So it's a constant pressure heat capacity. Second of all, I think it has more of a I don't know, a cadence to it. When you say it out loud, Q equals MC sub P delta T, and that helped me learn this formula more. That's just a me thing. It may not be a you thing, but the P is not that important. You don't have to write it if you hate it. It's just if you think it's helpful, I suggest using it. Also on this page, you have a lot of specific heat values for different elements. Now let's just look at a couple. Let's look at gold, for example. We know gold is a very good conductor of heat and electricity, and that correlates to low values of the specific heat. Things that are good conductors, we're going to have very low specific heat values. On the other hand, if we scroll down and look at water, water has a very high specific heat capacity. One of the highest of common everyday substances. And it's because of the water being a poor conductor. We know that if you're gaining heat, that means the particles are going to have to move faster. For water, that means they're going to have to overcome hydrogen bonds. And that's not easy to do. So when we add energy into water, we don't get an immediate change in temperature. We have to slowly overcome hydrogen bonds to make the particles go faster, and we see that reflected in a very high specific heat value. Let's do some actual problems now. I'm going to work through these problems. Go through them, hit pause, think about what you see written. Make yourself a list of questions. If you don't understand something I've done, bring that list in for tutoring, and let's see if we can get all your questions cleared up. In the first problem, we have, you can read it, calculate the change in temperature a 25 piece of granite undergoes when 15,400 joules of energy flow into it. Remember, our equation is Q equals M C sub P delta T. So all we do is plug into this equation and solve for the missing variable. In this problem, delta T is our missing variable. So we are going to plug in 15,400 joules. We're going to plug in 25 grams. Let's get rid of this. A better room. Okay. From the table on the previous page, the specific heat of granite is 0.790 joules per gram degrees Celsius. And delta T is our variable. You can make that an X, whatever you want. So just some very simple algebra. Divide 15,400 by 25 and then by 0.719, and we get 780 degrees Celsius equals delta T. Now, just a quick disclaimer. As I made these practice problems up, I wasn't really thinking about sig figs. Most of my sig figs here would round to just one sig fig. That's too much rounding in a lot of cases, so I try to hold to sig figs, like this number 1 is actually okay. But as we go into problems 2 and 3, if we rounded it correctly, it would be pretty nasty. So we're going to just pay some scant homage to sig figs for this. Number 2, calculate the heat capacity of water. And 625 grams of water is heated from 10 to 50. So this time we're still looking for Q. The mass is 625 grams. From the table, water has a very large specific heat of 4.184. This is not exactly what's on the table. 4.184 is the one I memorized in college. 4.184 is also the conversion factor from joule to calorie. So I'm not going to be memorizing a new number just because that chart had a little slightly different number. And then in this case, delta T, we were given from 10 to 50. The way we write that is final minus initial, so it's 50 minus 10. That's very important because if you got it backwards, you would get a negative value here, and that would show an exothermic reaction. But this clearly says water is heated. That's endothermic, so we would expect Q to come out to be positive here. So be very careful as you assign final and initial values in your delta T calculations. So we do all this, and it comes out to be 104,600 joules. Joules are very tiny. So I went ahead and divided that by 1,000 to convert it to kilojoules. It came out to be, if you round it, not to the correct sig figs, but just sort of a more normal number, 105 kilojoules. Joules are very tiny, so you really don't see joules that often. Kilojoules are much more commonly used for energy. In problem number 3, I'll use 15 kilojoules of energy to heat a 100-gram sample, initially at 25 degrees Celsius. What is the final temperature? So we're going to dive inside that delta T term a little bit here. So we have 15 kilojoules. Make sure you get that out of kilojoules and into joules if your specific heat is going to be in joules as well. That's what really makes the difference. So 100 grams of iron. From the table, iron is 0.450. See, this is the joules that made us have to get out of kilojoules from that property. And then this time, we're looking for TF if we start at 25 degrees Celsius. So there's just one additional algebra step this time. We have to divide 15,000 by 100 and then divide that by 0.45. And then we will add 25 to that. Take the moment, do the algebra yourself, see if you can get it right. I got 358 degrees Celsius as the final temperature. If you round it to the 1 sig fig, it goes up to 400, and that's just awful. So I'm just going to leave it as 358, even though that is not the correct number of sig figs here. And number 4, we're going to try to plug in some numbers here and calculate the specific heat of zinc. Just match it to the chart, see how close our numbers get. So this time we have 3.7 kilojoules of heat. Again, make sure you get that into joules. So 3,700 joules. We have an 800 gram sample. We're going to find that specific heat. And the delta T here, it says zinc changes 12 degrees Celsius, so that's all we need to plug in. Simple algebra here, specific heat comes out to be 0.385 joules per gram degrees Celsius. I think the table has 0.387, so we're really close. If you get it that close in the lab, you should be pretty proud of that, because that is an extremely small error. And then the last example problem using Q equals MC delta T, we're going to find an initial temperature. Again, just trying to do something different here. See all the little algebra ins and outs we could possibly do. I'm going to add 25,000 joules of energy to the sample of gold. This time we're given 5 kilograms of gold. That's another pitfall. we can't plug in kilograms, we have to plug in grams. So change kilo to gram, again, if our unit's going to be joules over gram degrees Celsius. So from the table, gold is 0.126. And this time we're looking for initial temperature, so it's going to be 35 minus Ti. It's very important you get that correct. The final temperature is 35 minus Ti. If you didn't do it that way, you would get the wrong answer. Alright, so just working this one in steps because the algebra is a little bit, not hard, but just unusual. So we have 39.68 equals 35 minus Ti. That's just from dividing 25,000 by 5,000 and 0.26. Then to get Ti by itself, minus Ti equals 4.68, and then that means the initial temperature here was negative 4.68 degrees Celsius. And if you wanted to round that one to sig figs, about negative 5 degrees Celsius. Alright, so that was just some real basic practice using the Q equals MC delta T formula. These now are real calorimetry problems where we use the concept here. Remember this concept. Heat lost by something is gained by something else. Heat lost equals heat gain. So this is where, think back to the picture from the other video. If the system is going to lose heat, something else has to gain it. And number one, a 50-gram piece of aluminum is dropped into a cup of water. So when we look at this, the aluminum is going to be our system. And the cup of water can be thought of as the surroundings for this problem. If we do it that way, it'll work out very simply. The way the equation set up then, the heat loss is going to be aluminum, so I'm going to have minus Q of aluminum times the specific heat of aluminum times the final temperature and minus the initial temperature of aluminum. Now TF is the same for both, that's why I didn't put aluminum on that. Water is going to gain this heat, so we will have, oops, I made a mistake. So back to this formula here, let's get the eraser out. Let's just pretend those last few seconds never happened. And let's redo that. Okay, so this is going to be minus, because aluminum is losing the heat, mass of aluminum, specific heat of aluminum, and then TF minus TI for aluminum. Water will gain this, so we'll have mass of water, specific heat of water, and then again TF minus TI of water. Alright, plugging in the numbers here, I got minus 50 grams. I'm going to save a little time here and not write all the units out. From the previous problems, I hope you believe how the units work out at this point. Delta T is what we're looking for, the change in temperature of the aluminum. We have 100 grams of water in this problem. The specific heat is 4.184, and the delta T is 5 degrees Celsius. So this one's very easy to solve to get delta T. We just simplify this side over here and then divide by negative 50 times 0.9. Delta T comes out to be, in this case, negative 46.5 degrees Celsius, which you could round to negative 50 if you want with sig figs. Same deal with sig figs on these problems. I didn't really do a good job designing these problems. But let's talk quickly about the sign here. This negative sign is very important because we're talking about the delta T of the aluminum. Aluminum is the hot item here. Heat always flows from hot to cold. So the aluminum is going to be losing energy. This is an exothermic process for the aluminum, and the sign is negative for the heat, and your delta T will be negative to correlate with that. Okay, on the next problem, we have a 1.2 kilogram block of silver, heat it to 150 degrees, and then we're going to put it into some water. And the water is initially at 20. What is the final temperature of the water? Well, remember, the final temperature is going to be the same for the silver and the water, so don't let that confuse you. In this problem, we do have something a little different. We're given a volume of water, not the mass. We're using specific heats, which means per gram. I do need to turn that 1 liter of water into mass. We can use the density, but the first thing we'll do is take this 1 liter and make it 1,000 mils. That's just a quick metric conversion. Then I'm going to take this 1,000 mils and I'm going to multiply it times the density, 1 gram per milliliter. Milliliter cancels, and that gives me 1,000 grams of water. Now, many of you probably could have done that in your head, but that's how we get that. The equation here is the same. The silver is the hot one. So in our setup, we're going to give a negative sign to the silver side. 1.2 kilograms of silver is 1,200 grams. Make sure you get to the proper units. From the table, 0.126 is the specific heat. And we are looking for TF starting at 150. I wrote the wrong number down. Let's fix that. And I also wrote the wrong specific heat down, so let's fix that. Alright, let's try that again. From the table, the specific heat is 0.233. And we are still trying to find TF, starting from 150. Okay, so the water here we have, as we calculated before, 1,000 grams, 4.184, and I'm running out of room a little bit, so I'm just going to write here TF minus 20. I'm going to go through the way I do the algebra. It may not be the way you do it, but I find this to be a fairly efficient way to do it. I'm going to simplify both sides first and get negative 280 times TF minus 150. And that's going to equal 4184 times TF minus 20. At any time, stop this. Make sure you follow the algebra. Alright, now I'm going to divide both sides by negative 280. And I'm going to get TF minus 150 all by itself. That will equal negative 15 because I rounded just a little bit there, not much. TF minus 15. I don't know why I just wrote 15. Alright, so that should have been 20. Okay. And I'll distribute out here. That equals 15 TF plus 300. Now rearranging that to get 16 TF equals 450, and then the final step is to get TF equals 28.1 degrees Celsius. Quite a bit of algebra on that. I guess that's the one bad thing about calorimetry problems is that the algebra, that's pretty typical actually for a calorimetry problem. All right, number 3 is a very similar problem. We're just not going to use water this time. Just kind of give you a different concept of system and surroundings. This time we're going to have a big block of granite, and then we're going to put a little piece of gold on it. And this time the gold is hot, so we're going to have energy flowing from the gold to the granite, and that granite is going to accept it. So our system in this case is really going to be, you could think of it as just inside that box. Nothing is leaving the system, we're just transferring energy within the system. With the same idea applies. If something inside the system loses heat, something else has to gain it. It must be conserved. So in this case, we have the gold, 1 kilogram, so 1,000 grams, and 0.126 is the specific heat, and this gold is currently at 80 degrees. Okay, and we have a 12,000 gram block of granite. With that much mass, we can go ahead and speculate that there's not going to be a lot of temperature change in the granite. There's just too much of it. TF minus 15. Now, what I suggest you do is hit pause, work through this algebra, and see if you can match the answer. It's going to be no new tricks here, so just hit pause and see how you do. Alright, let's check your work. If you got TF equaling 15.8 degrees Celsius, you did all of your algebra correct. And the last problem. We're going to take 30 grams of an unknown metal. So this is going to be calorimetry the same way, except we're going to figure out what the specific heat is of this unknown metal. It's a little different this time because the metal is only at 20 degrees and the water is actually at a higher temperature. So the water is going to be losing heat this time and not gaining it. It doesn't really mean much, except as I set up this problem, we've gotten used to maybe putting a negative sign in front of the metal's information. I'm actually going to put the negative sign in front of the water's information this time, since the water is losing the heat. My variable is C sub P. The final temperature here is 78.9. Remember, the final temperature of the water is the same as the metal. At thermal equilibrium, same temperature for both. Alright, now the water, we have a negative sign, 50 grams, 4.184, and 78.9 minus 80. And you're thinking, wow, that's not much of a temperature change. Nope. Water has a very high specific heat, so you don't get much of a temperature change. So just sorting through all the algebra here, rearranging your variables, or your numbers, you get the variable by itself. The specific heat comes out to be here 0.130 joules per gram degrees Celsius. And if you look at your table trying to pick out your best answer, you've got a couple that are pretty close. I believe the closest is lead. I think it was 0.128. That's pretty close. Tungsten was like 1.126 or something like that. That's also pretty close and well within the errors that you would get from a lab project. I guess the only thing I want to mention here that I haven't mentioned in any of our problems is the units of the specific heat. So take a quick look back on the screen. Every time I've written it so far, it's been joules per gram degrees Celsius. And if you look on your chart, a lot of them are 0.130, for example, joules per gram Kelvin. And I want to let you know that is exactly the same thing, because a change in degrees Celsius is equal to a change in Kelvin. That's because the formula to get between the two is plus 273. And let's just say you raise the temperature of something in Celsius by 40 degrees, you're going to do the same thing to the Kelvin scale because you're just adding to both sides. So a delta T in Kelvin is the same as a delta T in Celsius. You can use those two interchangeably. That's delta T now. I'm not saying Celsius and Kelvin are equal. I'm saying a change in Celsius is equal to a change in Kelvin. If that doesn't sit with you well, come by and we'll do some examples of some real numbers on that, and I'll convince you that's the case. All right, if you have any questions, come by and see me.